Dams. Dam is a structure built across the river or stream to hold water. People have used different materials to build dams over the centuries. Ancient dam builders used natural materials such as rocks or clay. Modern day dam builders often use concrete. Man-made dams create artificial lakes called reservoirs. Reservoirs can be used to store water for farming, industry, and household use. They also can be used for fishing, boating, and other leisure activities. People have used dams for many centuries to help prevent flooding. The ancient Mesopotamians may have been some of the first human to build dams. The oldest known dam is the Java Dam, located in present-day Jordan. It was built in the 4th century BCE. Dams provide farmers with a steady source of water to irrigate crops. This allowed ancient Mesopotamians to feed a growing population. They used dams to divert water for drinking, bathing, and irrigation. One of the oldest dams still in use is the Cornabo Dam in Spain. The ancient Romans built it in the 1st or 2nd century. The force of flowing water creates mechanical power. People have harnessed this power for centuries with the use of dams. Small dams powered paddle wheels in pre-industrial Europe and America. These were used to help sow logs or grind corn and other grains. During the Industrial Revolution, engineers began to build bigger dams. This industrial size dams could hold back more water to power the big machinery of factories and mines. They also could turn giant turbines to generate electricity.
My topic is Principle of Archimedes. The upward buoyant force that is exerted on a body immersed in a fluid, whether partially or fully submerged, is equal to the weight of the fluid that the body displaces and acts in the upward direction at the center of mass of the displaced fluid. Like for example, nagagis ka ng isang bato sa tubig, tapos yung impact ng pagbagsak ng bato, magkakaroon ito ng buoyant force, which is ito yung persa ng tubig pataas. Kagaya na lang dito sa image, makikita natin na may bagay dito na tumitimbang ng 7 pounds. Tapos nung inilagay niya nung ibinaba niya yung bagay na yon, nabawasan ito ng 3 pounds at yung tubig tumaas at nabawasan din ng 3 pounds. And they have a formula. FB is equal to P times G times B. FB is the buoyant force. P is the density of the fluid. B is the submerged volume. G is the acceleration due to gravity. And I have a sample problem. If a stone of mass 250 grams is thrown in water, calculate the buoyant force acting on it. Given mass is equal to 250 grams or 0.25 kilograms. 1 kilogram is also 100 grams, so 250 grams divided 100 kilograms is equal to 0.025 kilograms. And also known, our gravity is 9.8, and F is equal to mg. Substitute the value. 0.25 times 9.8 is equal to 2.45 N. 2.45 N of upward force is acting on the stone.
So, dadapo naman tayo sa stability of floating bodies. The stability of a floating object is defined as its ability to return to its neutral position after the external force has been applied and moved. So, mostly ang application nito ay sa barko. So, ang pinaka-importante dito sa part na to ay yung meta center. Kasi ito yung magdedetermine kung unstable or neutral ang floating body. The meta center is a point on the vertical neutral axis through which the buoyant force always acts for a small angles of field. So, parang linear lang ang location buoyant force at meta center. Kung small angle lang pero kung large angle ng tilt, the meta center may move along the neutral axis. So, ito yung sinasabi niya na small angle. Meron tayong buoyant force na mag-a-act ito yun. BF. Buoyant force. Yung weight natin ay always mag-a-act sa center of gravity based on loading. So, yung G na to, ito. Ay magbe-base on loading. Kung may mga cargo ka dyan sa barko, dun mo makukuha ang center of gravity. Meron tayong tinatawag na metacentric height. That is mg. So makikita naman dito ang MBO minus GBO kapag ang sagot dito ay positive. Bale, mas malaki ang MBO kaysa sa GBO, greater than sa top ng G. Pag ito ay equal, pag ito ay equal to 0, that is neutral. Kapag naging negative naman, so ibig sabihin mas malaki ang GBO. So yung G above ng M could be unstable states. So ito yung sinasabi ko. Itong part na to, ito yung G below is M. Meron tayong tinatawag na restoring moment. Ayun yung tutulong para ibalik niya yung floating body natin in neutral axis. MBO greater than GBO. M is above G, stable. Yun yung stable. Ito naman, MBO less than GBO, M is below G. Ito yung tinatawag na unstable. MBO equal to GBO, M is at point. Ito yung critically stable. Ito pala yung gagamitin nating formula. If the body has the shape of rectangular parallel pipe, MBO equal to B square divide 12D 1 plus tan square theta divide 2. Ayun po yung gagamitin nating formula para masagutan natin yung dun sa example ko. Mas mainam nang i-memorize natin tong formula na to para masagutan natin yung hinahanap sa page 2 dun sa example. So meron pa lang example dito. Rectangular scow 9 meter wide, 15 meter long and 3.6 meter high has a drop in seawater of 2.4 meter. Its center of gravity is 2.7 meter above the bottom of the scow. Determine the initial metacentric height. Itong nakasulat dito, yung nakadrawing, yan yung nasa page 2 na diniscuss ko kanina. So, bago simulan, ayusin muna tong sample. Yung B is 9 meter. And then, yung D, drop is, yung drop naman ay 2.4 meter. So, ibig sabihin, this is 1.2. Kasi, ito yung tubig ay yung kalahati nito. Tapos, yung the center of gravity is 2.7. Ito yon. Burahin. .7 above the bottom of the skull. So, yung height naman nito ay 3.6. Ito yun. Height. Tapos ang length naman nito ay 15 meter long. Kapag natapos na nating naayos, i-solve na natin. Isusulat ko na pala yung formula dito. Dito na lang sa taas. Yung MBO equal to B 12 1 tan square divide 2. Ayan, nakasulat na. So, ang kailangan na lang dito ay i-substitute natin. MBO equal, yung base ay 9. 12. Tapos yung drop 2.4. Tapos copy na lang to. Ayan. Ayan, ang susunod dyan yung hanapin yung MBO ito. Kung paano yung kinalabasan ng solving nito. MBO equals, sagot dyan ay 2.81 meter. Solving the GBO. So, ito yon 2.7 minus itong drop is equal to 1.5. 1.2 to 1.5. Then yung metacentric height naman is, yun yung gusto natin makuha. MBO minus GBO. Yan yun. Itong MBO, ito na pala yun. So, solve ko na pala dito. 2.81 meter. Tapos yung GBO naman ay 1.5 meter. Pero ang hinanap kasi ito, itong MG. Pag maminusin mo lang tong So, mg. Itong 2.81 minus 1.5. 1.5 equal 131 meter. So, ang sagot dito sa MGI, ito yung hinanap natin ay 1.31. Ayan, 1.31. That is. Yun na pala yung tinatawag natin na initial metacentric height. Ito na yun. Ito na yung answer.
So, dako tayo ngayon sa hoop tension and circular pipes and tanks. So, hoop is a ring or circle that is used to bind a barrel. So, bali ito yung example ko sa barrel. Ito yung hoop na humahawak sa kanya. So, para siyang isang sintron na hinihigpitan ng isang bagay para hindi ito masira. So, dako tayo ngayon sa hoop stress. So, hoop stress is a normal stress in the tangential azimuth direction. So, hoop stress is a stress that unmeasured degrees clockwise from the north direction. So, shear stress usually now. So, next is that you have your hoop tension. So, ito yung hoop tensions natin. Hoop tension is the force exerted circumferentially perpendicular both to the axis into the radius of the object in both direction and every particle in the cylinder wall. So, sa madaling salita, ang hoop tension daw ay nangyayari when there is shearing. Sakalang nagkakaroon ng isang hoop tension sa ating circular pipe sa ating barrel when the shearing is present. Ano ba ibig sabihin ng shearing? Hindi ba ito yung pagkapunit, pagkatir, pagka-split ng ating material? So, once na hearing or there is a shear present in your pipes, on your tanks, therefore, doon lang na-expose yung hoop tension in your hoop stress. So, sa hoop tensions natin, pag-uusapan natin ang dalawang stresses. So, the first is circumferential tangential stresses. Bali, ito yung example na drawing ko sa kanya. Ito yung sa pressure, ito yung sa formula. PD over 2T when your P that will be your pressure at yung D ay inner diameter. In your T that will be the thickness of your circular pipes on your thumbs. So, imagine itong tank here that is filled with fluid or gas under pressure that it is subjected into a tensile force. So, kapag ang ating circular pipe or circular tanks is filled with fluid, ibig sabihin nagkakaroon ng pressure sa loob. So, bali ito yung mga example na nakuha natin sa kanya. So, dako tayo ngayon sa longitudinal stress. Bali ito yung example na drawing sa kanya, tapos ito yung sa formula. So, PD over 40. So, ang ating longitudinal stress is same lang ng explanation ng circumferential stress. The only difference between the two is that kung ang circumferential stress or yung tensions or stress ay nangyayari kapag ang tearing apart o kung yung acting niya is longitudinal. Pag sinabi naman natin lang ng longitudinal stress, ang kanyang pag-shear is vertical. So, bali ito yung example natin sa kanya. Yung sample question natin sa hoop tension. So, question, steel pipe having the diameter of 36 inches carries water under the head of 750 feet of water. A. Compute the internal pressure on the pipe. B. Compute the wall thickness of steel pipe needed to resist the static pressure if the allowable stress for steel pipe is 16,000 psi. So, C. Compute the tangential forces on the steel pipe 4 inches. So, ito yung figure niya. Ito yung drawing. 750 feet, 36 inches. And ito yung example solution niya na nakuha natin sa kanya. So, dako tayo sa pangalawang example niya. Ito yung question. A vertical cylindrical tank is 6 feet in diameter and 10 feet high. Its sides are held in position by means of 2 hoops, one at top and one at bottom. The tank is filled with water up to 9 feet. A. Compute the hydrostatic force at the side of tank. B. Determine. So, ito yung figure niya. Ito yung example din solution natin sa kanya. So, bali dito nagtatapos ang aking report sa hook tensions in circular pipes and tanks.